We saw earlier that a system can be defined as the combination of system elements which interact to achieve a defined mission. Now, since each of these system elements will need to perform functions that have been allocated to it so it can contribute to the system's mission, we can consider a system to be a hierarchical composition of system elements. In a logical description of a system, the system's mission is broken down into a hierarchical structure of its major functions. The logical description or architecture is therefore often called a functional hierarchy or a functional architecture. In a physical sense, we saw earlier that a system can be considered to comprise operational or end products and enabling products. The end products of the system are also normally described in a hierarchy. Here we use a simple four-layer hierarchy. We can say that the top-level thing is the system, and it comprises subsystems, each of which comprise a number of assemblies, each of which comprise a number of components. And this then forms a physical hierarchy of the system. There are other terms in use, but these are probably the most common. The application of these terms to specific situations and different examples also depends very much on the context of the situation and where within the overall project the system is being considered. For example, if we take the highest level of an aircraft system, we could consider that an aircraft contains, amongst other things, an engine subsystem, and that would comprise assemblies such as fuel tanks, pumps and lines, turbines, compressors, gearbox and hydraulic pumps, and so on. Now, from the viewpoint of an engine manufacturer, however, the engine could be considered to be a system, and it comprises fuel, power plant, hydraulic subsystems, and so on. The problem is, however, if we consider the engine subsystem to be a system in its own right, an implicit part of the definition of a system is it has to be able to stand on its own. By that definition, an engine is not able to be considered a system. It's only useful as an element of a system, that is, as a subsystem. It's probably better, therefore, to consider a system of interest to comprise a combination of interacting system elements, some of which may be systems in their own right. When the system of interest consists of only system elements that are systems in their own right, the system of interest is called a system of systems. Now, a system of systems has a similar architecture to that of a system. That is, both comprise elements that are interconnected. But there is a difference. And the difference is that the system of system elements are systems in their own right, so that they're managerially independent and operationally independent, and have probably been optimized for their own purposes before contributing to the purpose or the mission of the system of systems. Now, on the other hand, if we take the system, the subsystems in a system are not independent and only exist to serve the parent system. Subsystems are therefore invariably not optimal from their own perspective. That is, they could be better. But it's the system that needs to be optimized, not the subsystems. We'll return to this issue later. The distinction between systems as element of a system of systems and subsystems as elements of a system is therefore that the system of system comprises systems that have been optimized for their own purposes before joining the system of systems. On the other hand, a system comprises elements, the subsystems, that are not optimized for their own purpose, but have been optimized for the system's purpose. From the higher level perspective then, a system of systems is most likely not optimized because the elements, the systems, were first optimized for their own purpose before joining that system of systems. Now, system of systems and systems, the distinction becomes quite blurred. So in this course, we'll leave it alone. We're focusing on systems whose elements are all subsystems, systems that are systems genuinely in their own right. We can complete our introduction to the nature of systems by returning to one of the early observations that a system can be considered to be the solution of a problem. As well as viewing the system descriptions in logical and physical terms, therefore, it's common to consider the activities being undertaken throughout the life of the system to be either in the problem domain, the problem space, where we use mainly logical descriptions, or the solution domain or the solution space, where we use mainly physical descriptions. We'll see later that the activities in the problem domain, including the production of the logical architecture, are mostly the responsibility of the customer or the business owner. The solution domain, including the development of the physical architecture and the physical solution, are generally considered to be the responsibility of the organisation who's developing the system, and we call them the developer. So now we've completed our brief introduction to systems. In the next presentation, we'll look briefly at the life cycle of a system before we turn our attention to the principal focus of the course, systems engineering. If you're interested in reading further into the topics we covered in this presentation, you may wish to read the corresponding chapters in the texts associated with the course.